So root mean square velocity is usually given by this Greek letter, like this. Oops, sorry. This Greek letter here. I don't want to. Maybe. Okay. And then, or sometimes it'll be just listed as RMS, right? Either way, this is how we solve for it. We take the square root of 3 times R times T over big M. Capital M stands for molar mass. Okay, this particular equation has a few changes compared to what we normally like to work with. Okay, in this equation, we use the other R value, R.315 or 3145. Right? For this equation only, we use that change in R value. Okay. The other change is that molar mass is not grams per mole, it's kilograms per mole. So when we put in an M into this equation, it's going to have to be kilograms per mole. Those are all things that I will, I'm going to give you an equation sheet for your exam. So you will have that equation on there, and I'll point out those things, right? Use 8.3 and use kilograms per mole. So yes, you need to be familiar with it, but I will give you those reminders on your equation sheet as well. The final units of a root mean square velocity, or the velocity of a gas particle, is meters per second. Okay, meters per second. If I needed a molar mass for CO2, the regular molar mass is 44 grams per mole. So if I need it to be in kilograms per mole, I take 44 and I divide by 1,000. That makes it 0.044 kilograms per mole. Right? That's all I'm doing is taking my molar mass divided by 1,000. That makes it kilograms per mole. Okay, are we on the same page with that? So to go in this equation, you have to do a little something extra. This means root mean square velocity. So here is what we solve for, that U, but it's also called root mean square. So sometimes you'll see it as find the RMS of this, and sometimes you'll see it as find this lambda or U value. So I want you to see both of them.
With the U and RMS?
They mean exactly the same thing.
So if you find U,
that is finding the same thing as RMS. Right? RMS is like the name of it. The U is like the variable that goes with it. Okay? All right, here we go. Moving into effusion and diffusion. These mean two different things. Diffusion is when we have the mixing of gases in an open chamber, right? Like the room. Right? If somebody sprays perfume, eventually all of those perfume particles will be spread out throughout the whole volume of the room. Right? So that's diffusion. Effusion is the passing of gas through a small hole or an orifice into an evacuated chamber. So kind of like a vacuum type scenario. And so the rate of effusion, which is what we're going to be solving for next, is basically talking about how fast does the gas pass through that tiny hole. We don't really have an equation that we're going to use for diffusion, but we are going to look at how we solve for effusion. Or R1 over R2 equals square root of M2 over M1. So there's an inverse there. These molar masses are just regular, so grams per mole. On your equation sheet, you'll see that I have it just written as R1 over R2 equals square root of M2 over M1. Right, it means the same thing. This is something that's important here. The R value is measured in moles per second. So it's how many moles pass through that hole or pass into that vacuum per second. How many moles of that gas. Okay, that equation's on your equation sheet if you need it. Let's try this effusion example. The effusion of hydrogen gas through a tiny hole is 0.000533 moles per second. What's the rate of effusion of oxygen gas at the same temperature? So temperature doesn't play a role in the equation itself, but what has to be true is that both of these gases have to be at the same temperature in order for that equation to work. Okay, so in order for us to use that R1 over R2 equation, they have to be at the same temp. So we have hydrogen gas, which is that just H? H2, and that means oxygen gas is also O2. Okay, so it says the R value for H2 is 0.000533, and the R value for O2, we don't know. All right, that's what we're solving for. So I'm going to put that into my equation. 0.000533 over R of O2 equals square root of, then you need to make sure that since oxygen's on the bottom in the first, on the left, right? Oxygen's on the bottom, that means oxygen molar mass needs to go on the top on this side. It does not matter if we would have put an oxygen here, hydrogen here, there. We would have needed to put hydrogen on the top, then oxygen on the bottom, right? It doesn't matter which object is 1 and which one is 2. They just need to make sure they go opposite of each other in your proportion. Right? Are we understanding where this 32 and the 2 came from? Molar mass of oxygen gas and molar mass of hydrogen gas. Okay? So run the math on that and see what we get.